Welcome, and thank you for joining us. Please note that this AI-generated podcast is intended solely for general learning and educational purposes. While we strive to ensure accuracy, the AI may occasionally produce errors or incomplete information. We strongly encourage you to consult qualified professionals and conduct your own due diligence before making any legal, financial, or business decisions based on the content presented here. Also, if you find this content valuable, we kindly request you to like the video, subscribe to the channel, and activate the notification bell to receive updates on future episodes. Let's begin.
Welcome to the Deep Dive, where we cut through the information overload to bring you the essential insights you need to be truly well-informed. Today, we're plunging into a world that touches, well, pretty much every corner of our lives. Computer Related Inventions, or CRIs. Think about everything from the algorithms recommending your next favorite song to the AI optimizing traffic flow, or even the security behind your online banking. These innovations are just reshaping industries at breakneck speed.
They really are. And, this rapid pace means the legal frameworks, well, they have to constantly adapt. It's a fascinating challenge. How do you ensure genuine innovation gets protected, but also, prevent monopolies on just abstract ideas?
Absolutely. And that's our mission today, to unpack this complex landscape of patentability for CRIs. We'll be looking specifically through the lens of the Indian Patents Act, 1970, and its really critical Section 3K. This section basically outlines what cannot be patented in India. It draws some important lines. We'll be drawing insights from the official Guidelines for Examination of Computer Related Inventions, CRIs, draft version 2.0, and its detailed annexure, which has a whole list of examples.
Those guidelines are crucial. They give the practical framework for how examiners at the Indian Patent Office actually approach these cases. They aim for consistency, clarity, which is tough in such a fast-moving tech world.
So why does this matter to you, our listener? Well, whether you're an innovator, a tech enthusiast, maybe prepping for a critical meeting on IP, or just, curious about how this cutting-edge tech actually gets protected, this deep dive is your shortcut. We'll show you how the law tries to distinguish between a truly inventive technical solution and, say, mere automation or just an abstract idea. And there are some surprising facts in here, those real aha moments. So what does this all mean for innovation's future? Okay, let's unpack this.
Let's start right at the core then with Section 3K of the Patents Act, 1970. This section, it specifically lists 4 categories that are excluded from patentability. These are mathematical methods, business methods, algorithms, and computer programs per se.
Okay, mathematical methods, business methods, algorithms, computer programs per se. That sounds pretty broad, like it excludes a lot of software stuff.
It can seem that way initially, but the key, especially for computer programs, is that little phrase, per se.
Per se. Latin, right, meaning by itself or in itself. That sounds small, but significant.
Immensely significant. You're right. It's a critical qualifier. Back in 2002, the Joint Parliamentary Committee, when they added per se to computer program, made it very clear their intention was not to reject all computer programs. They knew a program might include certain other things, ancillary thereto or developed thereon. The point was, if those certain other things are genuine inventions, they should be patentable. It's distinguishing the abstract code from the program doing something technically inventive.
Okay, so I think I'm getting it. It's less about the lines of code themselves and more about what that code achieves, the effect it has in solving a real technical problem.
Precisely. And that leads us straight to the really central principle in Indian patent law for CRIs now, the technical effect or technical contribution test. The Delhi High Court, back in 2019, in the Farid Alani case, really cemented this. They said, if an invention demonstrates a technical effect or a technical contribution, it is patentable, even though it may be based on a computer program. That was a huge clarification. It shifted the focus from the form, is it software, to the outcome, what technical result does it produce?
That's a massive deal for software innovators, isn't it? I mean, software isn't automatically out, but there's often this idea, this misconception that you need new physical hardware to patent software-related stuff. I think the Raytheon case addressed that.
Yes, a very important point. The Raytheon decision explicitly stated that requiring novel hardware lacks any legal basis. That was vital. It underscored that the focus must be on the technical outcome or effect. It doesn't matter if it's running on existing general-purpose hardware like your phone or computer. The contribution can absolutely come from innovative software.
Right. And the more recent Microsoft technology licensing case from 2024, that seems to build on this, right? It said the invention on a general purpose computer must contribute directly to a specific incredible technical effect or enhancement beyond mere general computing processes. It really has to significantly enhance the hardware's functionality. So not just automating, but making the computer itself work better technically.
That sums it up perfectly. It's about improving the machine's operation. And digging a bit deeper into what counts as technical effect, the ab initio technology case offered more clues. It said a technical effect is more than just the usual user interface. It could be an innovative input, something that lets the processor give a more efficient and faster output in computation. So the innovation might be in how data goes in, or how the system processes it internally, leading to real performance gains, making the computer itself better or controlling the physical world better.
Okay, so the goal is always substance over form. Does it solve a technical problem using technical means for a technical effect? With that foundation, let's break down each of those 4 exclusions in Section 3K. Let's see how this technical effect idea works in practice using those guideline examples. First up, mathematical methods. When we talk about a mathematical method exclusion, what does that actually mean? Is it any use of math?
No, not any use. A mathematical method under Section 3K refers to purely abstract or intellectual methods. Think methods of calculation, formulating equations, finding roots. Basically, the math itself, devoid of a practical technical application. But, and this is important, the mere presence of a formula doesn't automatically kill the patent claim. The Microsoft case in 2024 clarified that.
Right. So if the math formula is just one part of a bigger technical process that does something concrete in the real world, it might still be patentable.
It's exactly. The guidelines point out that exclusions might not apply if the invention uses math formulae, but results in, say, systems for encoding data, reducing noise in communications, or encryption-decryption. The key question during assessment is the core invention the abstract math processing itself? Or is the math an intermediate step within a larger technical process achieving a technical goal? Is the math doing a technical job?
Let's make that concrete with some examples from the guidelines, starting with the ones that are patentable, where math goes beyond just calculation. Okay, example 21, method for adaptive noise cancellation in audio devices. The claim uses FFT, inverse FFT, digital filters, all math heavy, for noise reduction, outputting clean audio to a speaker.
The core objective isn't just to calculate an FFT, it's reducing background noise in real-time audio devices. The math tool's FFT filtering are intermediate steps. They're part of a broader technical process, signal enhancement. And critically, the output isn't just a number. It's a technically improved audio signal delivered to a physical device, the speaker. That tangible technical outcome listed out.
Okay, that makes sense. Math serving a physical purpose. What about controlling something physical, like a drone? Example 22. System for controlling an autonomous drone. Sensors detect obstacles. A processor uses Dijkstra's algorithm for path planning, and it generates control signals for the motors.
Right. Dijkstra's algorithm is mathematical, finding the shortest path. But here, its job is autonomous navigation and real-time obstacle avoidance for a drone in the physical world. The algorithm is an intermediate step. The main goal is real-time physical control of the drone. The output isn't just a path calculation, it's control signals making the drone's hardware move. It's a technical solution for controlling a physical thing.
So it's about the context and the result. Is the math just math, or is it enabling a technical function? Let's look at another one. Example 23, method for image enhancement in medical imaging devices. It takes raw MRI data, applies wavelet-based denoising, reconstructs, and displays an enhanced image for diagnosis.
Again, wavelet denoising is a mathematical operation. But the objective is improving MRI image quality for medical diagnostics. The math is an intermediate step. The primary goal is clearer, more accurate MRI images for doctors to use. The output is a tangible, enhanced medical image used for real-world diagnostic decisions. Technical application.
And one more in this vein, example 24. Method for real-time vehicle stability control. Sensors feed data, formulas calculate slip ratios, control signals adjust braking and throttle.
Same logic. The objective is maintaining or restoring vehicle stability. The math calculations are intermediate steps. The primary goal is the technical effect real-time adjustment of braking and throttle to keep the car stable. The output is control signals directly affecting the vehicle's hardware. Tangible, physical control.
Okay, I think the pattern is clear for patentable mathematical methods. It's about application and tangible technical outcomes. Now let's flip to the non-patentable side to really see the contrast. Example 25, method for calculating compound interest. Input principal, rate, time, apply the formula, output the result.
Pure calculation. The core objective is just to perform a financial calculation. The computation is the end goal. There's no technical process, no transformation, no application beyond the math itself. The output is just a number. Classic abstract mathematical method, excluded.
Makes sense. And similarly, for example, 26, system for statistical data analysis. Input data, apply regression, output coefficients.
Exactly the same. The objective is performing a statistical computation. The computation in the end goal. No technical process beyond the math. Output is just numbers. Excluded.
And example 27, method for generating random numbers using a formula.
Also excluded. The core objective is generating numbers using math. Computation is the end goal. Output is just a sequence of numbers, no broader technical application defined.
Final one here, example 28, method for solving quadratic equations. Input coefficients, apply the formula, output roots.
Textbook mathematical method. Core objective to solve an equation with a formula. Computation is the end goal. Output numbers. No technical process or application. Excluded.
So the line is really bright here. If the math is the invention, it's out. If the math is a tool within a technical invention producing a technical effect, it can be in.
Got it. Okay, moving on to the next exclusion. Business methods. This one feels particularly relevant today with so much tech tied to commerce. How does India define and treat these?
Right. A business method is seen as covering the whole gamut of activities in a commercial or industrial enterprise relating to transaction of goods or services. Now, here's the really crucial point that distinguishes India from, say, the UK or Europe. In India, the exclusion for business methods is absolute.
Absolute. Wait, does that mean the per se qualifier we just talked about for computer programs doesn't apply here? Exactly. That's the critical difference. Unlike computer program per se, the term business method in Section 3K stands alone. The Delhi High Court in the OpenTV Inc. case was very clear. The exclusion in respect of business methods is an absolute one and is not restricted by the words per se. This means, essentially, that no amount of technical effect, clever implementation, technical advancement, or contribution can rescue something that is, at its core, just a business method.
Wow, that's a very strong stance. So it doesn't matter how technologically sophisticated the implementation is. If the fundamental invention is a way of doing business, it's out.
That's the essence of it. The core question examiners ask following OpenPV Inc. is, does the invention primarily address a business or administrative problem with a solution for that same kind of problem? Or does it primarily provide a technical solution to a technical problem using technical means, where the business context is just the field of application? It's about the fundamental nature of the contribution.
Okay, let's see this absolute exclusion in action with the examples. First, the ones deemed patentable because they're fundamentally technical despite the business context. Example 29. Secure data transmission in online banking. It talks about quantum-resistant crypto, secure channels, multi-factor biometric authentication.
Here, the invention's purpose is clearly to improve the technical robustness of data transmission and access control. These are engineering solutions to technical problems, data security, user authentication. Online banking is just the application domain, the place where this technical solution is needed. The invention isn't a new way to structure bank accounts or fees. It's a technical improvement in security. Patentable.
Right. The invention is the security tech, not the banking itself. What about hardware used in business, like a payment terminal? Example 30. POS terminal with adaptive signal processing. Claim mentions a dynamic signal processing module adapting to noise for reliable card reading, plus an error correction protocol.
This aims to improve the technical reliability and robustness of POS terminals. It tackles technical challenges in signal processing, reading the card reliably despite noise, and data transmission, sending the data without errors. It's a technical enhancement of the transaction infrastructure. Again, the invention is technical, not a business strategy. Patentable.
Makes sense. Improving the tools of business, not the business rules themselves. One more patentable one. Example 31. Optimize server load balancing for e-commerce platforms. Monitor activity, dynamically allocating resources with predictive analytics, rerouting requests.
The goal here is optimizing the technical performance and reliability of the e-commerce platform's server infrastructure. It addresses technical challenges in distributed server management, real-time load balancing. It makes the underlying computer system work better, faster, more reliably. That's a technical solution, even if it supports a business. Patentable.
Okay, the distinction is becoming clearer. Now let's look at the examples that fall foul of the absolute business method exclusion. Example 32. Tiered bank service fee calculation. determines balance volume, applies a tiered fee structure based on business rules, debits the fee.
The core objective here is implementing a scheme for revenue generation and customer management. It's purely an administrative and financial strategy. Using a computer to calculate and debit the fee is incidental automation. There's no technical innovation in how the banking system operates at a technical level. It's just applying business rules. Non-patentable.
Right. The invention is the fee structure, which is a business rule. What about loyalty programs? Example 33. Loyalty rewards program management, awards points, offers membership levels, provides discounts based on those levels.
Again, the core objective is structuring and operating a customer retention and engagement strategy. It's a marketing and administrative strategy. The computer is just used to track points and apply rules. No technical invention. Falls squarely under business method. Non-patent.
And dynamic pricing, like surge pricing for ride-sharing, example 34. Dynamic pricing strategy for ride-sharing services. Monitors demand supply, applies business rules for surge pricing, updates, fair quotes.
The core objective is optimizing revenue and managing demand through pricing. It's an organized commercial strategy. The use of computers to monitor data and apply the pricing rules is automation of a business strategy, not a technical solution to a technical problem. Non-patentable.
So with business methods in India, it really boils down to the fundamental purpose. Is it a way of conducting commerce or administration? If yes, it's out, regardless of the tech used. That absolute exclusion is powerful. Okay, let's tackle the third exclusion, algorithms. This feels like it overlaps with computer program per se, but it's listed separately. What's the distinction here?
It's a subtle but important distinction. The Madras High Court, in the Microsoft case, defined an algorithm as basically a set of rules or instructions for solving a problem, typically through a sequence of steps. The key distinction for patent exclusion is that algorithms are barred if they are presented as abstract concepts or just sequential procedural steps without enough technical implementation detail.
So if I just describe the logical steps of, say, the quicksort algorithm on paper, that abstract description isn't patentable.
Exactly. It's just an idea, a set of logical steps. The guidelines stress the need for specific enabling details to solve a real-life problem. It needs to be transformed into a practical innovation rather than a hypothetical sequence. It needs to show technical realization or application within a technical framework to provide a technical solution to a real-world problem. As the Delhi High Court noted in the BlackBerry case, if the algorithm is then implemented in software, coded for a purpose, and results in a technical effect, then the test for computer programs applies. The invention becomes the implementation, not the abstract algorithm itself.
Okay, so it's about grounding the algorithm in a specific technical context and showing how it produces a technical result. The assessment seems to be, are the steps purely abstract, or are they technically enabled with specifics to solve a real-world technical problem? Let's look at examples where algorithms are patentable because they're technically enabled. Example 35, secure biometric authentication for mobile devices. It mentions capturing a fingerprint with a capacitive sensor, extracting features using a CNN algorithm in a secure enclave processor, encrypting with a hardware AES engine, matching encrypted templates, and granting access.
See, this isn't just an abstract match fingerprint algorithm. It describes a technical workflow with specific technical components. The sensor type, the secure enclave, a specific hardware security feature, the hardware encryption engine. It addresses the real-world technical problem of securely authenticating users and protecting biometric data on a mobile device. The CNN algorithm is embedded within this technically realized solution. That makes it patentable.
That hardware integration really makes the difference clear. What about processing video data? Example 36, real-time video compression in surveillance cameras. Capturing frames with a CMOS sensor, motion estimation algorithm running on an FPGA-based hardware accelerator, encoding with H.265 codec, transmitting wirelessly.
Again, far from abstract. Each step is tied to specific technical components. The CMOS sensor, the FPGA, is a specialized chip for fast processing, the specific H.265 codec. It has a clear, real-world application surveillance and solves the technical challenge of efficiently compressing and streaming video over limited bandwidth. The algorithm is implemented in a hardware-accelerated end-to-end technical system. Patentable.
Okay, another one in a different field. Example 37, adaptive noise cancellation for hearing aids. Microphone array captures audio. A DSP executes an adaptive filtering algorithm. Amplifier and speaker deliver processed audio.
This is a technical solution for real-time noise suppression, specifically in hearing aids. It specifies concrete technical components, the microarray, the digital signal processor, DSP, amplifier, speaker. It shows the technical realization of the algorithm interacting with hardware to produce cleaner sound for the user. Addresses a real-world technical problem in a specific device. Patentable.
And one more. Example 38. Low latency packet routing in 5G networks. Receiving packets at a base station router, applying a dynamic shortest path algorithm using real-time network congestion metrics from distributed edge nodes, forwarding packets, updating tables.
This is a technical solution for efficient adaptive data routing specifically in high-speed 5G networks. It involves real 5G network infrastructure, base stations, edge nodes, and dynamic adaptation based on real-time conditions. It's not an abstract routing algorithm. It's a technically enabled process embedded within the network architecture itself. Patentable.
Okay, the theme is consistent. Concrete implementation, specific technical components, solving a real-world technical problem. Now, the contrast. Non-patentable, purely abstract algorithms. Example 39, generic sorting algorithm. Describes quicksort. Select pivot, partition, recursively sort, combine.
Just a sequence of abstract steps for sorting numbers. It lacks any specific technical implementation details or context showing how it solves a particular real-world technical problem, like, say, optimizing database performance in a specific way. It's detached from a practical technical framework. Pure algorithm, non-patentable.
And example 40, text tokenization algorithm. Scanning for delimiters, splitting a string, outputting tokens.
Similar situation. It's a sequence of abstract steps for text processing. It doesn't specify technical implementation details or how it's used within a specific technical context, like a real-time scooch engine, or solves a particular technical challenge. Abstract, non-patentable.
So, for algorithms, the invention lies in the specific technical application and enablement, not the abstract mathematical or logical steps themselves. All right, finally, the fourth exclusion. Computer program per se. This is probably the one people grapple with most often. We know per se is key, meaning not all programs are excluded. What's the definitive test here?
The core test, consistently applied now, is, does the invention provide a technical solution to a technical problem through technical means, resulting in a technical effect that goes beyond a mere incidental effect? As the Madras High Court reiterated in the Microsoft case, you don't need novel hardware, but the program must tangibly improve the system's functioning and efficacy.
So it's really about whether the software makes the computer itself technically better or controls something external in a technically improved way, not just using the computer as a tool for a non-technical task.
Exactly. The assessment process involves construing the invention, identifying the essential technical features, figuring out the core problem and solution in their technicality, and then crucially deciding if that technicality leads to a technical effect beyond just, say, being faster than doing it by hand. If it produces that genuine technical effect, it's generally not excluded under computer program per se.
The guidelines give helpful tables contrasting technical effect versus incidental effect. Let's explore some aspects that suggest a patentable technical effect. What kind of things qualify?
Well, things that boost the internal efficiency or functionality of the computer system itself. Think faster data processing due to innovative algorithms interacting with system architecture, more efficient storage systems like improved caching, optimizing memory use, or improved security like better encryption or intrusion detection that analyzes network traffic technically. Also, enhanced management of computational resources, maybe reducing execution time in high-performance computing.
Okay, so improving the computer's inner workings. What about controlling things outside the computer?
That's another major category, providing precise, improved, or adaptive control over machinery robots, 3D printers, making them maneuver more efficiently. Improving signal reception or transmission, like better noise filtering. Real-time monitoring and control of devices using sensor data, like in IoT systems operating physical equipment. Embedded code dictating specific hardware actions, like optimizing power use in an IoT device. Or generating control signals for autonomous vehicles based on real-time sensor data.
And what about concrete technical implementations?
Yes, things like medical image analysis using inventive algorithms that lead to a technical outcome, like better diagnosis potential. Optimizing data synchronization or fault tolerance in distributed systems. Simulating complex technical or physical systems, like fluid dynamics. Efficient training methods for ML models or novel neural network architectures designed for specific technical tasks. Efficient signal processing techniques solving a technical problem. All these point towards a tangible technical improvement.
That's a pretty comprehensive list of positive indicators. Now let's look at the flip side. What does tend to fall under the exclusion, seen as mere automation or lacking technical contribution?
The most basic exclusion is claiming software just by its storage medium a program on a disk. That's clearly out. Also, methods for organizing data that are detached from a technical process, like a new file format that doesn't actually improve storage or retrieval efficiency. A big category is the simple conversion of manual tasks to computer execution without adding any technical gain beyond the computer's inherent speed. Think automating bookkeeping, managing employee schedules, generating standard invoices.
So just making a manual process faster on a computer isn't enough.
Generally, no. It lacks that inventive technical contribution. Also excluded are inventions mainly focused on presenting data visually or textually without a technical solution in how the data is handled or displayed, standard business reports, a new layout for weather info. Inventions embodying rules for games or mental exercises like a new chess variant or a Sudoku solver. Things that mimic human reasoning without specific technical implementation leading to a technical effect, like a basic expert system giving generic advice. Inventions primarily concerned with aesthetics or artistic creation. Methods for medical diagnosis based only on symptom correlation or rule-based logic that just mimics a doctor's thought process without technical processing. Simple information retrieval using standard queries like a basic keyword search engine. And the guidelines explicitly mention customized playlist generation based solely on user preferences or listening history as lacking technical effect on the system.
That playlist example is interesting, very specific. Okay, let's make this concrete with examples. Patentable ones first, showing that technical effect. Example 41. System for adaptive traffic signal control. Uses image sensors, a central processor with a trained neural network, a dynamic signal control module commanding traffic lights.
Right. This integrates hardware, sensors, lights, with intelligent software, the neural network. The technical effect is tangible. Optimizing urban traffic flow, minimizing congestion, enhancing safety. It's controlling physical infrastructure based on real-time data analysis. Clearly technical.
Example 42. Method for data compression and cloud storage. Combines intelligent data segmentation, a context-aware compression algorithm, distributed storage logic.
The technical effect here is improved storage efficiency, bandwidth optimization, reduced latency, lower energy consumption for the cloud infrastructure itself. The context-aware algorithm makes the system technically better at storing data. Patentable.
Example 43. Method for error correction and wireless communication. Adaptive error correcting code selection, parity check module, selective retransmission.
Technical effect. Reduced retransmission overhead, improved network efficiency, enhanced reliability, energy savings in wireless systems. It makes the communication protocol itself technically more robust and efficient. Patentable.
Example 44. Method for efficient memory management in embedded systems. Real-time monitoring, dynamic reallocation based on predicted demand, compaction algorithm.
This directly addresses the internal workings of a resource-constrained embedded device. Technical effect. Optimize memory utilization, reduce fragmentation, improve device performance and reliability, lower power consumption. Makes the device work better technically.
Patentable. Example 45. Method for secure IoT device communication. PKI authentication, lightweight crypto, periodic key rotation.
Technical effect. Prevents unauthorized access, ensures confidentiality integrity, mitigates attacks, enabling secure and scalable IoT deployments. It improves the security and technical operation of the IoT network. Patentable.
Example 46. System for automated drone-based crop monitoring. Drone with multispectral cameras, processor with image analysis algorithms, vegetation indices, ML, reporting module.
This leverages technology for a specific technical task in agriculture. Technical effect. Improved agricultural productivity, resource efficiency, scalability, providing real-time insights for intervention by analyzing sensor data in a novel way, controls a physical drone, and provides technical analysis. Patentable.
Example 47. System for real-time fraud detection in financial transactions, transaction monitoring module, processor with trained ML model, alert module.
Technical effect. Reduces financial losses, improves detection accuracy, enables real-time protection, enhances operational efficiency in financial systems by technically analyzing transaction patterns, improves the security and function of the system. Patentable.
Example 48. Method for efficient spectrum allocation in wireless networks. Spectrum sensors, dynamic assignment algorithm, conflict resolution algorithm.
Directly impacts the technical performance of wireless networks. Technical effect. Higher network throughput, reduced interference, improved quality of service, scalability, makes the network operate more efficiently. Patentable.
Example 49. System for real-time network intrusion detection. Packet inspection module, processor with deep learning model, alert module.
Enhances network security at a technical level. Technical effect. Prevents cyber attacks, improves detection accuracy, enables real-time protection, enhances operational efficiency, technically improves network function. Patentable.
And example 50. Method for hierarchical token-based secure access for industrial automation. Secure channel, zone access token, time-limited device command token, validation for commands to physical sensor actuator.
This addresses the technical problem of securing control over physically distributed industrial equipment. Technical effect. Enhanced security, reduces unauthorized commands, controlled access, layered permissions, real-time authorization. Solves a specific technical problem in industrial control systems. Patentable.
Okay, that covers a wide range of applications where the technical effect is clear. Now, quickly, let's look at the non-patentable examples under computer program per se. Example 51, method for scheduling employee shifts. Automates collecting availability, applying rules, notifying staff.
Classic automation of an administrative task. Solves an organizational convenience problem, not a technical one. No technical effect on the computer system itself beyond basic speed. Non-patentable.
Example 52, system for generating business reports. Automates collecting, organizing, formatting, presenting sales data.
Again, automation of a business administration task. Presenting information. No technical improvement beyond inherent computer capabilities. Non-patentable.
Example 53, method for creating digital art. Automates color palettes, randomization for artistic output.
Primarily aesthetic artistic creation. No technical improvement to computing or image processing itself. Falls under aesthetic and copyright domain. Non-patentable.
Example 54, system for managing personal finances. Automates recording expenses, budgeting, charts.
Automation of personal information management. Non-technical problem. No technical improvement to the system. Non-patentable.
Example 55, method for generating playlists based on user preferences. Automate selecting songs based on preferences.
Solves a non-technical convenience problem. Explicitly noted in guidelines as lacking technical effect on the system. Non-patentable.
Example 56, system for generating invoices. Automates entering data, calculating totals, exporting PDF.
Automation of a business administrative task. Simple conversion of manual tasks. Non-patentable.
Example 57, method for scheduling social media posts. Automates receiving content time, queuing, posting.
Automation of an organizational convenience task. Simple conversion. Non-patentable.
Example 58, method for generating Sudoku puzzles. Automates selecting numbers based on rules, arranging in grid.
Creation of a mental exercise game. Explicitly excluded as rules for games or mental exercises. Non-patentable.
Example 59, system for managing customer loyalty points. Automates recording purchases, calculating points, redeeming.
Automation of a business administrative task. Falls under business methods and administrative automation. Non-patentable.
Example 60, method for generating email templates. Automates selecting templates, entering recipient info, sending.
Automation of an administrative communication task. Simple conversion. Non-patentable.
Okay, the pattern for non-patentable examples is also quite clear. Automating existing manual, business, administrative, or purely informational tasks without a core technical improvement. Now, this is all complex enough with existing tech, but how do these principles apply to the real cutting edge? Things like AI, machine learning, deep learning, blockchain, quantum computing. This must be where it gets really interesting and challenging.
Absolutely. These emerging technologies are, at their heart, built on abstract mathematical models and algorithmic principles. So the core challenge for patentability remains the same, but maybe even sharper, distinguishing the theoretical construct from an implementable technical solution. The focus, again, is on practical application, providing a technical solution to a technical problem through technical means, and crucially, with sufficient details for reproducibility without undue burden.
Let's start with AML-DL-related inventions. A really fundamental question is about inventorship. If an AI creates something novel, can the AI be named the inventor?
Under current Indian law, no. The Patents Act requires the inventor to be a person. AI systems, however advanced, are not considered legal persons. So inventions generated autonomously by AI are not patentable due to lack of a valid inventor. However, AI-assisted inventions, where humans use AI as a tool in the inventive process, can be patentable, provided they meet all the usual criteria, including demonstrating that technical effect, and the human inventor is named.
That's a critical clarification. The human is still key. Now, with AI, there's often a black box element, or claims can seem speculative. How does the sufficiency of disclosure requirement play out here? You need to really show how it works, right?
Exactly, and it's a high bar. Because AI can seem almost magical, the disclosure needs to be rigorous to enable someone skilled in the art to reproduce the invention. You can't just say, use AI to solve problem X. You need specifics. The Caleb Suresh Motopally case emphasized this strongly. The court stressed that the application must fully and particularly describe the invention and disclose the best method of performing it, enabling reproducibility without undue levels of experimentation.
So you really have to open the black box to some extent. The guidelines provide several scenarios for AML. Let's look at a few. Scenario 1. Input-output transformation. The example is example 9, translating handwritten prescriptions to electronic records using deep learning. What detail is needed?
You'd need to disclose the specific neural network architecture layers, activation functions, etc. Characterize the training data set, how collected, annotated. Detail the pre-processing steps, explain the training loss functions, optimizers. Provide validation metrics showing it works reliably. The technical effect is automating digitization, reducing errors, improving speed in clinical workflows. It's a technical solution to a data problem.
That's quite detailed. What about scenario 2? Trained AI model as the invention. Example 10 is a failure prediction system for industrial machines using RNNs trained on sensor data.
For the trained model itself to be the invention, you must explicitly identify the training data and explain its link to the technical problem, predicting failure. Disclose the model architecture, LSTM layers, time window, and the training methodology. Provide performance results, proving it reliably predicts failures. The technical effect is early accurate anomaly detection, reducing outages, optimizing maintenance, concrete technical benefit.
And scenario 3, where data preprocessing is key. Example 11 is crop classification using satellite imagery, where cleaning enhancing the data is crucial.
Here, you need to detail the entire pre-processing pipeline step by step. Explain why this pipeline improves results compared to using raw data. Describe the CNN model parameters, training data characteristics, and provide comparative performance benchmarks. The technical effect is large-scale, high-accuracy crop classification, enabling better land management.
It seems like the level of detail required is substantial, really demanding that the inventor explains the how. Let's shift gears slightly. What about quantum computing-related inventions? This field feels even more theoretical in some ways.
The principle is the same. Abstract quantum principles, superposition, entanglement are not patentable in themselves. Patents are for real-world, tangible applications showing a concrete technical effect or improvement. Sufficiency of disclosure is key, often requiring details about the physical hardware and how the abstract principles translate into tangible applications. Take example 17, hybrid quantum classical computing system. It claims a QPU with specific transmon qubits, a classical control unit using ML for feedback, a compiler, cooling systems, etc. To be sufficient, it needs details on the qubit design, the ML control architecture, the cryogenic setup. The technical effect is enhanced fidelity, minimized decoherence, increased performance of the actual quantum computation. It's about the implemented system.
And example 18, chip-based photonic quantum computing device. Claims a silicon photonic chip with specific components like waveguides, single photon sources, detectors.
Right. The disclosure needs specifics on the chip design, component integration. The technical effect is creating a reconfigurable CMOS-compatible platform, enabling high-speed, low-noise quantum operations with enhanced gate fidelity and scalability. Again, tangible hardware implementation.
Okay, finally, blockchain-related inventions. What's the approach here? Is it just about distributed ledgers?
No, again, abstract blockchain principles aren't patentable. It's about the real-world application showing a concrete technical effect. How does blockchain solve a specific technical problem? Sufficiency requires detailed descriptions, cryptographic techniques, specific data structures used, the consensus mechanism chosen, interaction with hardware or networks. Consensus mechanisms and data layouts are particularly important. Consider example 19, computer-implemented method for executing a rental agreement over blockchain. Claims deploying a smart contract, verifying crypto payments, generating digital access tokens, activating physical assets, immutable recording. Sufficiency needs details on the smart contract logic, how it triggers actions, and crucially, the protocols linking the contract to physical IoT hardware, like a door lock. The technical effect is automated enforcement of access payment, reduced fraud, and integration with physical devices for secure access. Technical solution, not just a ledger.
And example 20, decentralized system for supply chain provenance tracking, private blockchain, hybrid consensus, smart contracts for compliance, off-chain data anchoring, IoT sensor integration.
Disclosure needs details on the hybrid consensus, smart contract functions, the Merkle tree anchoring, and IoT integration specifics. The technical effect is low latency finality, real-time tracking, improved scalability, via off-chain anchoring, automated compliance checks, and secure monitoring of physical goods using IoT data on the blockchain. Solve technical problems in supply chain management.
Wow, okay. This deep dive has certainly unpacked a lot of layers in patenting computer-related inventions in India. I think the core takeaway really is crystal clear. While those specific exclusions exist, abstract math, pure business methods, standalone algorithms, programs per se, the door is very much open. It's open for innovations that demonstrate a genuine technical effect or technical contribution. It seems you really have to look beyond the code itself, see how the invention truly improves a system's function or solves a real-world technical problem.
Absolutely. And that technical effect, as we saw, can come from software on standard hardware. You don't always need brand new physical kit. The focus is squarely on the outcome, the technical improvement achieved.
And that substance over form principle is key, isn't it? Examiners are trained to look past the claim language to the fundamental nature of the invention. Is it really a business strategy dressed up in tech speak? Or is it a genuine technical innovation applied in a business context? That distinction is vital, especially with that absolute ban on business methods.
Precisely. And for those emerging technologies, AI, blockchain, quantum, the bar for disclosure is high, and rightly so. You need detailed technical enablement, demonstrable, reproducible effects. It's about distinguishing truly patentable applications from abstract concepts or just speculative claims. That ensures the patent system's bargain disclosure for exclusivity is upheld.
So, a final thought then. As technology keeps blurring the lines between digital and physical, and as AI gets more and more capable, how will our very understanding of what constitutes technical evolve? And what incredible new inventions might emerge from that expanded definition? Something to ponder. What kind of computer-related inventions are you, our listener, working on or curious about? How do these guidelines affect your view of innovation? We genuinely love to hear your thoughts.